Hi, everybody. So I hope you're getting a feel for just how important integration by substitution is and see that it's going to be an extremely powerful tool that we're going to use a lot through the rest of not just this course, but courses into the future. You may have noticed that we have not done a definite integral yet using U substitution, and we should do that. So here's an example of how we can make this work. So I have 1 over square root of some stuff. The stuff is that x cubed plus 1. So that's just screaming out to be somebody's u, right? I'm an x cubed plus 1. Hello, please make me be your u. And, and if we do let x cubed plus 1 be the u, the derivative is 3x squared plus 0, so I don't have to write that down. And sure enough, there's an x squared sitting right there. So we are good to go. We can do u substitution. The u would be the 3x squared plus 1. The du would be 3x squared. So du is 3x squared dx. I've got the x squared. So we're in perfect shape, right? The x squared and the dx will become 1/3, if I take the 3 over to the other side, du. So there we go. I have a 1/3 and a 1 over square root of u du. And that's something I can integrate because I know how to integrate a square root of u. I'll first make it u raised to the 1/2 power, and because it was in the denominator, it'll be negative 1/2 power. So then I can just integrate that with the power rule. U to the negative 1/2. I need to add 1 to the negative 1/2, which makes that plus 1/2. So I'll get u to the 1/2 power over 1/2. And now that looks weird. So if you want to just flip that denominator and make it 2 over 1, or just 2, I can multiply that in front. But that's exactly what that is. U to the 1/2 over 1/2 times the 1/3, which is sitting out in front. And so if I substitute the x cubed plus 1 back in there for u, then I end up with 2/3 and a square root of x cubed plus 1 plus c. And you may notice that all the way through this, I have not written my limits of integration. I've just kept it as an antiderivative problem. And the reason is, I think it's much, much, much simpler to do it that way. Because remember, how do you do a definite integral? The first step is to do an indefinite integral, right? Find an antiderivative. Then you deal with plugging in the endpoints. So I'm going to write this without any endpoints at all. In fact, when I got to the end, I have to write plus c for my answer. But then when I go back and try to solve the original problem that had endpoints, I just grab that antiderivative, 2/3 square root of x cubed plus 1. Then I plug in the 2 and the 0 and subtract, and you end up getting some number like 4/3. Okay? But this is really easy, but the place it's easy to make a mistake is if I, in the middle part of my screen there, had left the 0 and the 2 as my endpoints, even after I had switched to u's, that would actually be wrong. Because those limits of integration, the 0 and the 2, those are x numbers. See, those are bounds on x. If I wanted to write limits of integration as I was doing the u substitution, I'd have to convert those 0 and 2 numbers, which go with x, into different limits of integration that go with the u. Okay? So I think that's much, much more difficult. I think it's much better to do all your integrating, then go back and do all your substituting, right? All your plugging in of the numbers. But there are times when you need to know this rule. And so it's worth going through this to show you how to do it so you'll know how this works. So here's another way to do it, right? If I had wanted to do this, keeping the limits of integration there the whole time. So I would let u equal x cubed plus 1 again. The du would be 3x squared dx, so that's all fine. And I end up so far doing the same kind of substitution. I get 1/3 and 1 over square root of u du. But notice now, I kept writing the limits of integration. So I originally wrote limits of integration from 0 to 2. Now all of a sudden I have 1 and 9. Where in the world did the 1 and 9 come from? Well, that's why I don't like doing it this way. But it's important to know that you can, and sometimes you have to do it this way if the problem that you're working on, needs you to just change your integral and not necessarily solve it. So where did the 1 come from? Well, it's my lower limit of integration, and that's because the original lower limit of integration was a 0, right? Well, that 0 was an x number, okay? So I need to turn it into a u number. So how do you do that? Well, u is x cubed plus 1. So if I take x equals 0, right, and do my substituting, that would give me 0 cubed plus 1, and that becomes my u number of just 0 plus 1, or just 1. Same way with the 2. If x is equal to 2, then u, which is x cubed plus 1, becomes 2 cubed plus 1. 2 cubed is 8, so 8 plus 1 is 9. So there's where my new limits of integration come from. Now, again, I don't like doing this if my point is to actually do an integral, because I've had to stop in the middle of integrating to go plugging numbers in, right, to plug the 0 and the 2 into x cubed plus 3 in order to find the new limits of integration. And it kind of, messes with my flow, right, as I'm working through this problem. But it works. And there are definitely times when you're working with an integral and you just need to do substitution to change it into a different kind of integral. And knowing that this is how you do it is important. So how would I do it the rest of the way? Well, I'd move the 1/3 outside. I would integrate my u to the negative 1/2 and get u to the 1/2 over 1/2. And now, because I've already changed my limits of integration to be u numbers, I don't have to change it back to x's here, because that 1 and the 9 have already been turned into u numbers. So I just need to go ahead and plug those straight in there for u. So I would get, 2/3 square root of 9 minus 2/3 square root of 1. And when you do all that arithmetic, you get 4/3 again, which is exactly what we should have gotten from last time, right? It's exactly the same problem. Okay, so again, if this is more complicated, why would I want to know that? Well, what about a problem like this? So this problem tells us that the integral from 2 to 3 of, f of 5x minus 2 dx is 4. Okay? And then they ask us what's an easier looking integral. You just go from 8 to 13, but now it's just f of u du. Okay? Well, all right, I don't have any idea what f of u du is or how this works, but obviously there's got to be some reason why they asked it this way. And it is, right? If I take that original integral and I just start doing substitution to it. So I've got f of that ugly stuff inside, 5x minus 2. So if I let u be that 5x minus 2, du would be 5 dx. So if I solve this around, the x becomes 1/5 du. Then my original integral, f of 5x minus 2 dx, becomes f of u, and then 1/5 du. And now notice what happens when I change my limits of integration. Because it looked like these limits had no connection with each other at all, but of course they do. They're exactly what happens when you switch the limits of integration around. Because if x is 2, that lower limit of integration, when x is 2, u would be, 5x minus 2, that'd be 5 times 2 minus 2. That makes 10 minus 2 is 8. So when x is 2, u is 8. And what happens when x is 3? Well, 5 times 3 minus 2, that's 13. So sure enough, those are my limits of integration. So to finish off the problem, the original integral they gave us, which was 4, is equal to 1/5, what they're asking us about. So the answer is, the integral they're asking us about has to be 4, right? And then solve for that integral by multiplying through by 5. And the answer is 4 times 5, which is 20.